Hello, in our lesson today, let us discuss Stoke's theorem. This lecture can be divided into three parts. In the first part, we will try to understand the statement of Stoke's theorem. In the second part, we will understand the proof of the Stoke's theorem. And in the third part, we will see how Maxwell applied Stoke's theorem to arrive at his famous equations, Faraday-Maxwell's equation and Ampere-Maxwell's equation. First, let us try to understand the statement of Stoke's theorem. Informally, Stoke's theorem deals with flux of curl of a vector field over a surface and its relation with the line integral of the vector field along the boundary of that surface. So if you state more formally, then suppose we have a closed curve C and there is a surface S enclosed by the curve. And this surface is not necessarily a plane surface, it can be an uneven surface, whereas N is the positive normal from the surface. Now positive normal has the following meaning. For a closed surface which encloses a volume, positive normal goes outwards. But for open surfaces, there is a convention. The convention is that if you walk along the boundary of the surface with the surface on your left, then your head will point towards the positive direction. So we have a positive normal. And there is a vector field A in 3 dimensions introduced in the region where the closed curve exists. Then there exists the following very important relationship. It is stated as follows. The surface integral of the curl of the vector field along the surface S is equal to the line integral of the vector field along the boundary of the surface, and this curve C is the boundary of the surface S, whereas the surface S is enclosed by this boundary C. So this is about the statement of Stoke's theorem. Now we proceed to the proof of Stoke's theorem. So in left hand side we have a curl, that is curl of A, and we divide it into 3 parts. Curl of IAX plus curl of JAY plus curl of KAZ. This is easy because A can be divided into IAX plus JAY plus KAZ. And we will work with the term 1 and we will notice the symmetry of the result. And then by noticing the symmetry of the result of the calculation of term 1, we will be able to say what is term 2 and what is term 3. So here we take a 3-dimensional coordinate system x, y, z, and our curve is this curve A, C1, B, C2. This is a closed curve. And there is a surface which is enclosed by the curve. The surface is the surface S. The surface S is enclosed by this closed curve. And we also take a plane which is parallel to the YZ plane at a distance x from the y-axis. This plane P will intersect the surface S along the curve C1, C2. Along this curve C1, C2, the plane P will intersect the surface S. And we will integrate first along the C1, C2 curve, and then we will vary the C1, C2 curve from A to B. That is how we will be able to cover the whole surface, because we are interested in the surface integral. So we will have the following strategy. We will integrate over this curve C1, C2, and then we will vary the curve from A to B, and that way we will be able to cover the whole surface. Now term 1 is a determinant. and this determinant can be calculated easily. It is j partial derivative of x with respect to z minus k partial derivative of x with respect to y. And integrating term 1 over s, we get term 1 dot n ds, that is n dot j partial derivative of x with respect to z minus n dot k partial derivative of x with respect to y ds. Now over the curve C1, C2, I will try to find a relation between n dot j and n dot k. So now let us consider that plane P which is parallel to the yz plane at a distance x from the yz plane. And the plane P intersects the surface S along the curve C1, C2. We take an elementary area ds on the curve C1, C2, and on the elementary area the outward normal is n. Now because n is perpendicular to the differential surface element ds, if we project the differential surface on the xy plane, then we have this relation ds equal to dx dy divided by n dot k. In other words, n dot k multiplied by ds equal to dx dy. Now as on the curve C1, C2, the x coordinate remains fixed. If we travel along C1, C2, then the change in position vector is given by dr equal to j dy plus k dz, because x coordinate is fixed. That means dr is j dy plus k dz, and we know that dr is tangential to the curve C1, C2, whereas n is normal to the curve C1, C2. Therefore we have a dot product vanishing, that is n dot dr equal to 0 equal to n dot j dy plus n dot k dz. This is a relation that we have obtained between n dot j and n dot k. Now the surface integral is term 1 dot n ds, which has both n dot j and n dot k, and we have replaced n dot j in terms of n dot k and ds in terms of dx dy. So we have substituted ds as dx dy divided by n dot k, and in term 1 we had n dot j term, and we have replaced that n dot j term in terms of n dot k. Then term 1 dot n ds is a to b, that is from here to here, and then c1 to c2, that is here to here. That means we are first integrating over the strip C1, C2. Then after integrating, we are varying the strip from A to B. So A to B, C1 to C2, and here within the square bracket we have the expression of term 1 dot n ds, which is partial derivative of x with respect to z dz plus partial derivative of x with respect to y dy dx. We notice that this is nothing but the total change dax. So that is this d total change dax. So when dax is integrated, we get ax, and we can substitute the limits c1 and c2, but we have to take care of this minus sign. So ax at x, here is c1 dx minus x here c2 dx, because we have substituted the limit c2 and c1. So ax bracket x y1 z1 dx minus ax bracket x y2 z2 dx. Notice that x coordinate is the same in the first term and in the second term. It is because we are integrating over the strip C1, C2, which has constant x. So now we have a to b ax dx minus a to b ax dx. But this is not 0, because this is from the left arc and this is from the right arc. Because y1 z1 lies in the left arc and y2 z2 lies on the right arc. So this is not cancelling to give us 0. So what we can do, we can change this minus sign to plus sign by flipping these limits. So a to b ax dx along the left arc plus b to a ax dx along the right arc, which will give us integral over the whole closed curve a c1 b c2 a ax dx, which is the line integral, part of line integral, which is coming from term 1. So term 1 dot n ds is giving us integral over the closed curve c ax dx. So while substituting the integration limits, we have put x y1 z1 in place of c1 here and x y2 z2 in place of c2 here. That is, this is term 1 dot n ds. Now let us see what is term 2 dot n ds. Just from the symmetry, term 1 dot n ds equal to ax dx over the closed curve. So term 2 dot n ds is ay dy over the closed curve, and term 3 dot n ds is az dz over the closed curve. That means if we add this, right hand side becomes ax dx plus ay dy plus az dz, an integral of that quantity over the closed curve. So that is, we have a dot dr, that is in the right hand side we have integral over the closed curve a dot dr. That is the line integral. So this is a very strong result, that if you integrate curl of a over the surface ds, that result is equal to the line integral of a over the boundary of the surface. And this result was known by 1860, and in next 5 years Maxwell utilized this theorem to write two of his very important equations of theoretical physics. So we will see how Maxwell did that, how Maxwell used this Stokes theorem to write his important equations of theoretical physics. So first let us consider the Faraday's law. Faraday's law gives the rate of change of flux over a closed curve d dt of b ds del del t of b ds, and relates it with the EMF in the circuit, and this minus sign signifies that the EM is developed in the direction in which it opposes the change in flux. See, here we have a change in flux, this is flux, and this time derivative gives a change in flux, but this minus sign indicates that the EMF which is developed here will oppose the change in flux here. Okay, so we can easily use the Stokes theorem here. E dot dr becomes curl of E dot n ds, and right hand side is here, this is minus del del t of B dot n ds surface integral, and then because ds is arbitrary, we take this integral to the left hand side, so we get within the bracket curl of E plus del B del t bracket close, then dot n ds equal to 0, which gives us curl of E equal to minus del B del t, and this was Maxwell-Faraday equation, and Maxwell-Faraday equation is one of the Maxwell's equations, 4 Maxwell's equations, which Maxwell found in 1861. Next, let us look at the Ampere's law. Ampere's law says that if we take the line integral of magnetic field around a closed curve, and the current carrying wire is carrying a current IC, then Ampere's law is B dot dr equal to mu 0 IC. So here, if you have a current carrying wire, and if you take a curve which encloses the current carrying wire, and this curve is a closed curve, then the line integral of magnetic field over this closed curve is equal to mu 0 times IC. IC is the current flowing through this wire. Now we can write IC as IC equal to double integral over surface S j dot n ds, and this B dot dr using Stokes theorem can be converted to surface integral of curl of B. So these two equations together now will give me curl of B minus mu 0 j dot n ds equal to 0. because here is mu 0. So mu 0 IC will give mu 0 j. That means curl of P minus mu 0 j dot n ds equal to 0. And again, this ds is arbitrary. Because this ds is arbitrary, then we can write curl of P equal to mu 0 j. But in the electrodynamics, there is a problem. And we will see what is the problem. So if we take divergence of both sides, then we will get divergence of curl of B equal to 0 in the left hand side. The left hand side divergence is 0, but the right hand side, the divergence is not 0. The divergence is this quantity minus epsilon naught mu 0 del t of divergence of E. And this extra divergence in the right hand side has to be killed. And Maxwell did that. What Maxwell did, he added mu 0 epsilon naught del E del t in the right hand side. The divergence coming from here, which is, if you take the divergence of both sides, then the left hand side is 0 because divergence of curl of P, and right hand side here you have a divergence of J, and here you have a divergence of E. So these two terms will get cancelled to give you 0 identically. So this is the Maxwell's Ampere's equation, which uses the power of vector analysis, the Stokes theorem and the continuity equation to write down Ampere-Maxwell's equation. So the second term in the right hand side of equation 26 was discovered by Maxwell, and this term is called the displacement current. Thus, Maxwell neatly expressed laws of electrodynamics as a set of 4 differential equations. One is divergence of E equal to rho by epsilon naught. Second is divergence of B equal to 0. And the third and fourth equations we have derived here, Maxwell-Faraday's equations and Ampere-Maxwell's equation. So in doing so, Maxwell used the power of Stokes theorem. So here we have used the following references, Davies and Snyder. This is an old reference, but this is extremely good. And the Spiegel, Lipschutz, Spellman, this is a vector analysis book from Schom series. And then Arfken and Weber and Harris, this is a standard book of mathematical methods. In Emil Boas, we have used mathematical methods in physics, physical sciences. And then Potter and Goldberg, we have used in mathematical methods. So that means what we have done today is that we have learned the statement of Stokes theorem, we have learned the proof of the Stokes theorem, and we have also learned how Maxwell used Stokes theorem to write down 2 of his famous equations. First, we learned how to write Maxwell-Faraday's equation, and next we have learned how to write the Ampere-Maxwell's equation. So I hope this lesson was very useful for you. So I will also give the PDF file in the description box, and thank you for watching.